the question here, this is our example number 2. Can you remind me what this question is asking of us, please?
Determine the vertical deflection at joint C.
The deflection at C?
Yep.
And it's the vertical one, right?
Yes.
And in this case, did I also provide you with the answer for it?
Yep.
What was it?
0.133 millimeters.
Okay. And does it say up or down?
Down.
Down? And that way, you know, if you wanted to try this on your own ahead of time, you can, you could have, and see if you got the same answer, similar, different, why not? Now, if you remember, there were 4 basic steps to solving this kind of question, right? The first one was, given the truss we're looking to solve for, do its analysis, right? Method of joints, method of sections, graphical method, whichever method you pick. Then steps 2 and 3 were to essentially repeat that again, but do it only with one load, a load of 1 at the location where you want the deflection, right? So basically repeat the whole thing, but without the real loads, you put this virtual load of 1 at the location where you want the deflection. And step 4 is set up a table. You remember the table?
Yeah.
Okay. So this method, in itself, what you're learning is very, very small in terms of how much time it takes to solve a question like this. Because the majority of it is to solve the truss twice. Does that sound familiar? Is this coming back from what we did last week? Okay. So in this case, we have this truss. It's a triangular truss, a very simple triangular truss. Measures 8 meters in span, 3 meters in height. It has a 4 kilonewton force going sideways at C. We want to find the vertical deflection at C. So we have to do the big step 1, which is do the truss analysis and figure out the forces in every member. Okay? So I'll do this, and I'll make sure that I cover all the steps.
There's other variables.
There are some other variables?
Yeah.
For sure, yeah. What else do we have?
It says assume A equals 400 millimeters squared.
400 millimeters squared.
And E equals 200,000 MPa for all members.
200,000 MPa. And this is for all members?
Yes.
Okay, terrific. Can you remind me, what does A stand for? Right? So basically, if I were to take any one of these members and cut it across and look at it, it would be that area. So we're just told what the area is. At this point, we're not caring about the shape. What is E? Young's modulus, or modulus of elasticity. It's a quantification of how elastic a certain material is. Basically, this tells you if you had a material made out of something and you were to pull on it or push on it within a certain limit, how easily does it spring back before it doesn't do that anymore, right? That's what E is. Kind of like a spring constant, if you will. This number here tells me this is steel. It's structural steel, okay? You'll get to learn that this number is structural steel once you do the course next term. Okay? I believe John Cochran is doing structural steel design for you. Okay, anything else you want to add? No? Okay. Okay, so the first thing that I'm going to do then is do the truss analysis. So figure out the forces in every one of these members. So then within that one big step, you remember what the first thing to do is? Step number 1? Free body diagram, reactions, right? So I'm just going to sketch the reactions here. Based on this sketch that I have on this page, A is a hinge. So it comes with a Y reaction and an AX reaction. And B is a roller, so it comes with a single reaction which is perpendicular to the surface it's sitting on. So BY is like that. Does that look about right? Look okay? Then, let's start labeling this properly. I'm going to leave this room here for any answers I'm looking for. Just going to move to this side. And I'm going to write determine member forces. And I'm going to call this real load. Right, so that's the 4 kilonewton. So now that we have these reactions, and because we're at a point where this is your 4th structural course, can you tell me, for example, what is the value of AX?
Zero.
Minus 4.
So AX has to be exactly this amount, but in the opposite direction, right? Because it has to balance out. Now, I'm going to write it out fully, but we're at a point where this is the kind of thing that you could write down already, and I would accept. So in this case, we have AX plus 4 kilonewtons equals to 0, which gives us AX equals to minus 4 kilonewtons. So which way is AX going? It's going this way, right? Because we assume that way. So if it's negative, it's going the other way. Okay. Are we able to figure out AY and BY super quickly on the fly? Not so much. Okay. We could if this were a vertical load going down, but it's not. It's a horizontal one. So I'm going to be thinking carefully about this. If I do some of the forces in the y direction, all I'm going to get out of it is that AY is the same as BY, or something similar, right? That has 2 unknowns. So I'm going to do the moment equation first, because it's going to at least help me figure out one of the unknowns. What direction do you want to make positive for your moment? Clockwise or counterclockwise? Clockwise? Okay. We'll do that clockwise. And where do you want to do your moment about? Sure, why not? Any of the supports is a good place for it. Some of the moments with respect to A. So right here. So the moment equation becomes 4 kilonewtons times a distance of 3 meters minus, because this By is causing a counterclockwise moment, By times a distance of 8 meters. All of this equals to 0. Does that look okay? Okay. And then from this, if we rearrange it, we get that By is equal to 1.5, I believe. I get positive 1.5. Now, to be fair, I skipped a number of steps to go from here to there. I did them all up here. I'm okay if you do all the steps to get to here. What I want to make sure that is crystal clear is this should be true. You are able to go from this line to that line regardless of what steps you take. Is that true? Okay. So for this, I get By positive 1.5. So that means it's in the same direction I guessed, like this. Okay? So now that we know By, let's find out Ay. Sum of the forces in the y direction equals to 0. We have Ay plus By equals to 0. And I know that By is that. So how much is Ay?
Negative 1.
It's negative, right? So that means it's going in the opposite direction, I guess. Make sense? So I'm just going to summarize these answers over here. Ay equals to 1.5 kilonewtons down. By equals to 1.5 kilonewtons up. AX equals 2, 4 kilonewtons going that way. You don't have to do this. I'm simply doing it because, unlike you, I don't have an infinite amount of paper, right? I have to erase stuff. So I'm just making room and trying not to forget about certain amounts. May I erase this? Would that be okay? May I erase this? Okay. So now that we have these reactions, we can now go inside the truss, joint by joint by joint by joint by joint, and figure out all the forces inside the truss. Okay? Where do you want to start? We have 3. Where do you want to start? A, B, or C? Sure. Why not? Could you start at B if you wanted to? Could you start at C if you wanted to? For sure. In this case, yes, any of them is fine because, remember, you have to have no more than 2 unknown member forces to solve it. Okay. So we just pick A because why not? So I'm just going to do this nice and slow. I'm going to remind myself what A looks like. I'm going to sketch the members that go into A. I'm going to remind myself that this is AC. I don't know what it is, so I'm going to guess tension. This member here is AB. I don't know what it is, so I'm going to guess tension. And then on A, I'm also going to put on the reactions associated with A. So I know that AX goes this way, and it is 4. I know that AY goes this way, and it is 1.5. Is that okay for the free body diagram? Anything missing from here that we could do better? I'm sorry?
The degree.
This one here and here, huh? Because we know these ones, but we need to know what this is. So I'm going to call that angle theta. How much is it? We can do tan inverse of
304, 17.7.
like that.
36.87.
6.876.
36.87.
I wasn't even close. Okay. 36.87
87 degrees.
70 degrees like that.
Oh, you want 3?
When you do angles, you want at least 3 digits because it can make a big difference with trusses.
So it's 870, yeah.
870?
Yeah.
Going once? You like 870? Okay. Alrighty. Like this. So now we have a choice. We're either going to solve for AC or AB first, so do either X forces or Y forces. Which one is a good one to start with first? Y. If we do X first, both this and that will appear in it, right? Because they both either are 100% X or have a component in the X direction. If we do Y first, this is the only one that has anything related to Y. So we'll find it out. Make sense? Okay. Sum of the forces in the Y direction equals to 0. What do we have? We have AC times sine of the angle minus 1.5 equals to 0. Right? These two. So if I solve for this, it's AC equals 2 1.5 divided by sine of that. 36.870. And at this point, are you okay if I skip putting in the units until I get the answers? Okay. What is this number, please? Something like this,
4999.
right? So depending, regardless of where you stop, it comes out to be this, basically. Okay. How did I know that? Would you be okay if I stepped it up a little bit when it comes to this? To show you something you know already. Would that be okay? Sure. Okay. Notice this triangle. This is a 3, 4, 5 triangle, right? So I'm just going to sketch this here. And this is the angle we're looking for. This is 90 degrees, right? Okay. Now, let's try this. I'm going to write this down from here. Okay? I'm going to write my SOHCAHTOAs. So, sine of the angle equals 2. You remember what SOHCA is?
Opposite. Both sides.
3 divided by 5, right? Do you remember what co is, or ka?
Adjacent over.
Adjacent over hypotenuse. So it's 4 divided by 5, right?
Yeah.
So another way to do this sine of the angle is to simply do it, turns out exactly the same way, but just using the sides of the triangle. Sine of theta is sine of this angle, but it's also 3 divided by 5, right? So that's how I was able to see that if I put this in here, 3 divided by 5, this is actually exactly 2.5. The reason you get 2.4999999 is because you truncated the digits here. So this is just me showing you how you can bring it up to the next level. This is perfectly fine. Okay, perfectly fine. But I'm just building on what you already know. Now that we have AC, if we do the sum of the forces in the x direction, we can figure out AB. So in the x direction, we have minus 4 kilonewtons plus AC cos of the angle plus AB. All of that is equal to 0. I'm just going to add a 0 here. Okay, so we have the value of AC right there. And then we know that cos is either 4 over 5 or cos of that number. Make sense? Okay. Okay, so let's work this out. That means that AB is equal to 4 minus AC times cos of the angle. Okay. Where AC is this number here. What do you get for AB, please? A little louder?
2.0.
Right, if you do it with this, you get 2. If you do it with this, you'll get 2.000001. Sound about right? So, to keep track of this and keep it the same, I'm just going to write it down like this. Okay? Now let's go back a second. The fact that I got a positive number here for AC tells me that my assumption is correct. AC is in fact in tension. The fact that I got a positive number here for AB tells me my assumption is correct. I guessed it in tension. AB is in fact in tension. So we have found this member force, this member force. Okay, now we can go from A to any of the other two joints. Which one do you want to do? B? Is that what I heard? Okay. Next. B. So I'm going to sketch it here like this. Like that. CB. I have CB. I don't know what it is, so I'm going to guess tension. BA or AB. I do know what it is. So what I'm going to do is going to sketch it. Color AB right here. Okay. We do know what AB is. It's 2 kilonewtons in tension. So notice how I sketched it in tension already, because it's pulling on B. And lastly, we have BY. BY on B is up 1.5. That's what I put right here. That look okay? Okay, is this free body diagram okay with us? Is that okay? All right. So I think we can move on to then our equations of equilibrium. Let's do that. Which one do you want to start with first, X or Y? Did I hear Y?
Yeah.
Why not? Sum of the forces in the Y direction gives us CB. Okay, that's good. So we have CB times, do we need this angle here?
It's the same.
Is it the same? Because the geometry is the same, is it not? It's a
Yes.
4, 3, 5 triangle. Okay, so I'm going to call this CB times sine of that angle. And we also have 1.5 kilonewtons going up. So the Y component of CB plus the reaction vertically have to add up to 0 for this to be in equilibrium. For sine, you can either choose to do sine of this angle or replace it with 3 over 5, whichever one you would prefer. So then we get that CB is equal to minus 1.5 divided by sine of the angle. What is this number?
2.5.
Pardon me?
Negative 2.5.
Negative 2.5. And that's important, right? And just to keep the same convention, I'm going to add 2 zeros just to give the 3 decimal places. What does this negative mean? Right. I guessed it in tension. If I get a negative sign, that means the direction is incorrect. It's in fact in compression. Okay, are we done?
Redo it.
Go ahead. No. No. We have to do some of the forces in the x direction. Because we have to make sure that every joint is in equilibrium. That means all forces always balance out to 0. And this is a good habit to get into because it also goes along with the other same habit, which is always triple check your answers. Okay? All right. Some of the forces in the x direction. I get minus 2 minus CB times cos of that angle equals to 0. Look okay? Okay. So I'm going to substitute the number in here correctly, just so you see how I'm doing it. This is minus 2 minus 2.5 times cos of the angle. You can either write it as cos of this number or 4 over 5. It's fewer strokes if I write it as 4/5. So what do you get when you do this? -4?
Zero.
Okay, I'm hearing one is -4 equals to 0, and the other one is 0 equals to 0. Anybody else get a different answer? Please shout it out. So we, yeah.
You would have to put the coast in front of the 4.
No, you don't need it.
You don't need it, that's what he's doing it.
Oh, you do.
Anybody else get a different answer here? I am inviting you just so we can see. Okay. If you've gotten this number here, it might be that you forgot about these two negatives. Right? These two negatives become a positive, so this becomes -2 plus all of this is 2. Make sense? So in fact, what we do get from here is 0 equals to 0. Okay, could you do an experiment with me? Okay? Could you actually redo this, but instead of doing 4/5 for cos, can you actually plug in cos of this angle? What is the number we get on this side, please?
0.000002.
What's the last number?
2.
Like that?
Yeah.
Yeah. So this is an engineering 0 equals to 0. I would accept this if you gave it to me as an answer as well. Okay? All right, so now we have this member force. We've confirmed this member force. Are we done? Are we done?
We're done with this, but we have to move on.
Yeah, so we're not finished yet because everything has to be in equilibrium. We haven't checked to see if C is in equilibrium. I'm going to do it for the benefit of us practicing this, okay? So for C, C looks something like this. What do we have? We have CA or AC, which is this in tension. So it's this value here. .5 in tension. Okay? For CB, what do we have for CB? We have this in compression. So I'm going to draw it in compression. Like this. 2.5 in compression. And the last thing we have on C is the applied force of 4 kilonewtons, right? Like that. We also know that this angle is theta. We also know that this angle here is theta. Okay? So, from this, we would have to do our sum of the forces in the x direction, sum of the forces in the y direction, and spoiler alert, they work out. Okay? But you should do it. At our level right now, we're still not good enough to assume that this will work out.